Hello and welcome to section 5.3 on solids of revolution. As we learned in section 5.2, the volume of a solid can be calculated by first determining a function A, which represents the cross-sectional area through the solid, then integrating with respect to A. This just leaves us with the task of calculating the function A. In this section, we study solids of revolution. These solids are formed by taking a two-dimensional area and rotating it about an axis of rotation. These solids are special as we can use the axis of rotation to aid us in calculating A. In section 5.2, we introduced the washer method. Recall that the area of a washer is calculated as pi times the outside radius squared minus the inside radius squared. Take, for example, the region defined by the curves x equals y squared and x equals the square root of y. If we rotate this region about the line x equals 0, the y-axis, then we obtain the solid of revolution. Slicing perpendicular to x equals 0, that is, we choose a y value between 0 and 1, we obtain washer slices whose outside circle is blue, bounded by the curve x equals the square root of y, and the inside circle is orange, bounded by the curve x equals y squared. The radius of the blue circle for a particular y is the square root of y, while the radius of the orange circle is y squared. Therefore, the volume of the solid of revolution is calculated using the integral of the cross-sectional area A, which is the area of the washer, pi times the outside radius squared minus the inside radius squared. When calculating a solid of revolution, there exists an alternative method to washers, known as the cylindrical shells method. In this method, rather than taking perpendicular cuts along the axis of rotation, we will analyze how parallel slices of the original region contribute to the volume of the solid. This region was rotated about the line x equals 0, the y-axis, so a parallel line to the axis of rotation can be found by choosing a value for x. The slice corresponding to a chosen x value will be rotated about the axis of rotation, forming a hollow circular cylinder, commonly known as a cylindrical shell. Dividing the interval AB into n subintervals of length delta x and taking the midpoint xi, we can calculate the volume of such a shell if the shell has height represented by a function f, a width delta x corresponding to the thickness of the slice, and when unraveled, the length will be 2 pi xi, the circumference of the circle formed by this slice rotating about the axis. The volume of each shell can then be found as the multiplication 2 pi xi times f of xi times delta x. The volume of the solid of revolution can be approximated by the sum of the volume of each shell, Taking the limit as n approaches infinity, n being the number of slices, we find that the volume is represented by this Riemann sum, which is the integral from a to b of 2 pi x times f of x. To summarize, to compute the volume as an integral using cylindrical shells, we take a parallel cut to our axis of rotation and calculate the radius, or the distance, that the slice is from the axis of rotation, and we calculate the height of the slice. Let us revisit the region defined by the curves y equals x squared and y equals the square root of x, and let's rotate it about the y-axis, which is x equals 0. Choosing a slice of the region parallel to the axis of rotation, we choose an x value between 0 and 1. We then calculate the height of that slice. It's the top minus the bottom function, the square root of x minus x squared. And we calculate the distance the slice is from the axis of rotation. As the value x is x distance away from the y-axis, we find that the radius is x. Therefore, the volume can be found using the integral from 0 to 1 of 2 pi x times the square root of x minus x squared. In summary, we have two methods to compute the volume of a solid of revolution. To decide which to use in a particular problem, Remember that in the washer method, you must cut perpendicular to the axis of rotation. Ask yourself, can you easily describe the inner and outer radius of the washer formed by rotation? If not, then shells might be a better choice. In the shell method, you must cut parallel to the axis of rotation. Can you easily describe the height and radius for the resulting shell? If not, then washers might be a better choice.